Welcome to Hamadu Web. AI or not, understanding computer science topics still matters. Here, you learn to stay confident, competent, and in control. Every single day, we use numbers. But have you ever stopped to think about how they actually work? Today, we are breaking down the hidden language of computers. From the system you use every day to the code that makes this video possible. Let's start with what we know. Base 10, also known as denary. This is the system we grow up with. It means we have access to exactly 10 unique digits. We start counting at 0, we increment to 1, then 2, then 3, all the way up to 9. But here's the catch. We have just ran out of digits. So how do we represent the next number? We have to reset that 9 back to 0, add a new place on the left, and increment that to 1. Now we have 10. Let's keep going all the way to 19. Once again, we have run out of room in the last digit. We reset the 9 to 0, but looking at the first digit, the 1, we see it still has room to grow. So we increment the 1 to a 2, giving us 20. To really understand this, let's look at the number 124. Every digit sits in its own specific column based on the power of 10. The 4 is in the position of 10 to the power of 0. The 2 is in the position of 10 to the power of 1. And the 1 is in the position of 10 to the power of 2. Since 10 to the power of 0 is just 1, this means we have 100, 2 tens, and 4 ones. If you sum those up, 100 plus 20 plus 4, you get exactly 124. Now, base 2 or binary is the language of computers. In this world, we only have access to 2 digits. The exact same logic we just used applies here. We start with 0. The next number is 1. But now we have no more room to increment. So we reset the 1 to 0, add a new digit, and put a 1 in front. This gives us 10, which represents 2. Next, we increment the last digit to get 1, which represents 3. Now both columns are full. Just like before, we reset both to 0, add a new column, and mark it 1. Now we have 100. The next number is 101. But what is 101 in our human language? We use the 2's table. The far right is 2 to the power of 0, which is 1. The middle is 2 to the power of 1, which is 2. The left is 2 to the power of 2, which is 4. We have 1 4, 0 2's, and 1 1. Add 4 plus 1, and we see that 101 is actually equal to 5. Now let's get a little crazy. Base 16 or hexadecimal. Here we have access to 16 digits. We start at 0 and count up to 9. But we aren't done yet. Our next digit is A, which represents 10. Then B, C, all the way to F, which is our 15th value, representing 15. Now we are truly out of room. We reset the F to 0, add a new digit, and we get 10, which in hexadecimal actually equals 16. Let's try converting the hex number 43 into decimal. The 3 is in the 16 to the power of 0 column, the ones place. The 4 is in the 16 to the power of 1 column, the 16th place. So we have 4 16s, 3 ones. 64 plus 3 gives us 67. Guess what I found when I searched 67 meme on Google? So why binary? It turns out this is the fundamental building block of computers. A bit is the smallest way a computer can represent data. It is just a 0 or a 1. Think of it like a single character in a word. The next step up is a byte, or sometimes called a word, which is comprised of 8 bits. Computers generally read data word by word. This is actually where terms like 32-bit or 64-bit architecture come from. It represents the size of the chunks the computer processes. Half a bit is also called a nibble. This brings us to overflow. In languages like C++, variables have a fixed size. If you aren't careful, you will find yourself in a tricky situation. Let's say you have a variable the size of a byte. The highest number you can represent is 255. That is 8 ones in binary. If we try to increment this by just 1, mathematically we should get a 1 followed by 8 zeros. But because our variable is locked to 8 bits, that new leading one has nowhere to go. It falls off the edge. We are left with 8 zeros. Instead of 256, your program thinks the answer is 0. That is definitely not what we were expecting. Another place you see this math is in colors. For example, the color of this text is hashtag EBDBB2. This is a hex representation of RGB, red, green, blue. Each pair of letters represents a number between 0 and 255, telling the screen how much of that color to use. Using our 16s table from earlier, let's break it down. For EB, E is 14 and B is 11. 14 times 16 plus 11 gives us 235 red. For DB, D is 13 and B is 11. 13 times 16 plus 11 gives us 219 green. And for B2, B is 11 and 2 is 2. 11 times 16 plus 2 gives us 178 blue. That specific mix gives us this nice beige color. There are so many situations where knowing this comes in clutch, like understanding file permissions or debugging memory issues. On your coding journey, you will encounter moments where knowing how the raw numbers work will save your life. Remember, computer science is all about taking data, manipulating it, and returning the result. Ensure you do the manipulation right. I hope this helps make things clear. See you on the next one.